So today, I guess we're going to go through a tour of Ramsey theory, if you like. A particular part which deals with semigroups, so that's quite a common thing that comes up in Ramsey theory. So we'll see. Hi. Sorry. That's all right. Yep. So we'll just see a few examples of how semigroups arise in the Ramsey theory. It's simpler than you think. There's no high-powered machinery here. These happen to be semigroups. And we have Ramsey theory statements. And then hopefully we'll have time to see a generalization of some of these ideas that Martina, who's not here, and I have been working on over summer. We'll be clear about the same thing next time. All right, so first thing we'll talk about, what the hell is Ramsey theory? Many of you will be familiar, but some of you may not. Hi, Amber. So basically the idea of Ramsey theory, the general idea is what we do is we take some sort of structure, some mathematical structure, and we color its elements. So we can think of it as partitioning the structure as well. So either a finite partition or a finite coloring of the elements. Then what we want to find is a substructure which is monochromatic and has certain properties. Okay? And what those properties are depends on the theorem in question. That's what the structure we're looking at, and the properties of the substructure are what differentiate the different theorems in Ramsey theory. Cool. So probably the namesake example would be Ramsey's theorem, right? Which many versions of it. Here's one version. For every m, which is a natural number, whenever I say m and n, it's going to be a natural number. And k. Cool. And then for every finite coloring of the power set of the natural numbers, there is an infinite set, an infinite subset of the natural numbers, such that, how should I write this? All subsets of that set, all B subset of A that have size m are monochromatic. Okay? So fixed sum m could be like 4. Then you can find an infinite subset of the natural numbers, so that all 4 element subsets of that have the same color. Right. Now this theorem here, the only structure we've really got is the fact that it's a set, right? It doesn't even have to be the natural numbers. Any countably infinite set would work, right? The only important thing here is that it's a set. We don't use any count. Okay, so sometimes we'd want a bit more structure than that. Right? Sometimes it's interesting to look at things which have a little more structure. So we'll talk about semigroups then. That's the structure we'll be looking at. Okay, so in case you don't know what a semigroup is, it is a set S with a binary operation, star, and the only requirement we have is that this has to be a subset. Okay. So in symbols, that means that x star y star z is the same as x star y star z. Okay. Doesn't matter which way you break it. Let's see some examples of a semigroup. There's lots. Pretty basic one is the natural numbers with addition. Right, addition's associative. There you go, it's a semigroup. Okay. Same thing with multiplication is also a semigroup. Any group is a semigroup, right? Because one of the group requirements is got to be associative. Any ring is a semigroup. In fact, in two different ways, right? Because you've got two operations. I think they have to be associative, right? Trying to remember rings. So yeah, let's see an example which some of you may be new to some of you. So we take that's a set A, okay, and A is going to be an alphabet. So you can think of the elements of A as like something. Basically, what we're going to do is look at the set of all words, which is notated like this A star. So it's words over A. Like a word being just a finite tuple of elements of A. And then the operation would be concatenation. Cool. So if you have two words, you just put them into N. That's the semigroup operation. Right? That's true. And that you can think about it a bit, but concatenation is associative. This example is going to be relevant for a lot of the examples we talked about. This is known as either the word semigroup, or it's also the free semigroup. Okay, because it can be constructed in much the same way as a free group, if anyone's familiar with those. Cool. What else about semigroups? So just like in group theory, we also talk about homomorphisms of semigroups, right? Which respect the operation. So if we have semigroups S and T, then a homomorphism from S to T would be it's the usual thing, right? So if I omit the operation together, then it satisfies this. So it respects the group operation. It's the same in the domain as in the codomain. Okay, so an example for our word semigroup here. So if you have any function from A to itself, then that sort of induces a semigroup homomorphism on the free semigroup. S star to A star. Okay, which it's not too hard to see how it would. So if you have a word here, A1 up to AN, then you just map it to F of A1 up to F of AN. Right, so you just apply this function to every letter in your word. And that's a semigroup homomorphism. So it doesn't matter whether you concatenate here or here, you get the same result. Cool. At some stage, we may look at partial semigroups. So partial semigroup means this operation that we have isn't always defined. Okay, so there may be two elements of the semigroup where you can't define their product. In that case, we've got a notion of a partial semigroup being adequate, okay? Because basically we want to exclude trivial cases, like for example, if the operation is never defined, right? Then we couldn't really say much about the result. So we say a partial semigroup is adequate if for every finite subset of the semigroup, there is an element Y such that X star Y is defined for all X and A. Okay, so for every finite subset you can find an element in the semigroup such that you can define its product with everything in that subset. Okay, so that's what adequate means. All right, that's semigroups. If there's any questions at any stage, please interrupt me or put your hand up. Let's get on to the Ramsey theory then. Okay, so I think probably the earliest example of a Ramsey type theorem on semigroups would be what's called Hindman's theorem. Okay, and this is about our most familiar semigroup, which is probably the natural numbers with addition. Okay. So again, just like in Ramsey's theories, theorem, we're taking a finite coloring of our structure, which is the natural number. So, and we have a coloring, say an R coloring, where R is a natural number. So we color it with finitely many colors, then we can find an infinite subset of the natural numbers, such that, I'll write it like this. So basically, the idea is all sums of elements of this infinite subset. So all sums of elements of A, so x1, x, of distinct elements, you always get the same color. So it's monochromatic. So that basically the set of finite sums of elements in here is monochromatic. Cool. In fact, there's nothing special about the structure of the semigroup in question here. So this theorem actually generalizes to any semigroup. Okay. So we have an arbitrary semigroup. For all finite colorings of our infinite semigroup, we can find a sequence, infinite sequence of elements of the semigroup. Okay? Having the property that the product of any subsequence, of any finite subsequence, is the same color, monochromatic. Okay? So where it's got to be an increasing subsequence. That set is monochromatic. So I guess the reason for this restriction is that the operation might not be commutative anymore. Yeah, but any finite subsequence we can ensure its product is monochromatic. Cool. This one's sort of special in that the proof of this theorem was basically the first time that infinitary methods were used in Ramsey. So stuff like ultrafilters or non-standard methods, for those of you that done Martinez course. Cool. You want to know more? This is a, yeah, hi.
I was just going to say when. You said it's the first time?
Oh, 1974, I believe, from memory. Right, Ramsey theory is fairly new though. It's only really been a field since maybe the 1950s. Right, Ramsey's original theory dates back to 1930, but it didn't really pick up traction until, I guess, the work of British in the 50s. Now we'll look at this word semigroup we were talking about before, or a variation on it. Okay, so this one's called the Hales Jewett theorem. This is 50s, 1950s sometime. Okay, so we need a finite alphabet A, but it does have to be finite for this to work. Okay, and we're going to look at the word semigroup we're also going to look at, so let's say we have a variable symbol. Variable, let's call it V. And we're going to assume it's not an A. And then we're going to look at, I guess, the variable word semigroup, which would be all words which include V. Okay? So I'll call it V. If you want a definition, it would be A union V star subtract A star. Yep. So this is essentially all words over A, but they have to contain this variable. Okay? And the idea with the variable is probably what you think, right? We've got spaces in our word, and we replace that variable with a certain letter. Okay? So that's called the substitution map. So if we have an element, a variable word, an element of this semigroup here, then it gets mapped to what we'll notate like this. And A. Okay, and basically for every occurrence of V, our variable in here, it gets replaced with an A, right? So we have one of these maps for every letter in our alphabet. I make this X, actually. Let's use X as a variable. Cool. That's a semigroup homomorphism. Exercise to the reader. So what the Hales-Jewett theorem says, this is the finite version. It says, so for every finite coloring of the word semigroup, so the ones without variables, there is a word, a variable word, such that basically any possible substitution you can make here gives you the same color in this coloring, right? So you notate it like that. It's basically the set of all possible substitutions into W. Cool. The infinitary version says that, again, for any finite coloring, this time we can find a sequence, an infinite sequence of variable words, such that the following set is monochromatic. Okay, it's basically, it's similar to what we're doing over here, so taking finite products and like. So any subsequence and any possible substitutions into the elements of that subsequence, again, you always get the same color. So notation gets a bit messy here. This is notation for concatenation. Is monochromatic. So it has, again, it has to be an increasing subsequence, and there's A1 through AK length. So two versions. This one's a little simpler, right? This one is more powerful, okay? And this one implies this one by what's called a concatenation. Anyone who's done Math 309, I'm talking about curves. Right, sort of a standard way to go between finite and infinite version.
So with this infinite version,
yeah,
the letters that you're substituting in that bit for last time.
It's for any possible choice of letters.
Okay.
But finding that sequence is probably not easy. but you can do it. It exists. Okay. Similar thing, we're going to look at now what's called a generalization of this called the Graham-Rothschild theorem. Graham-Rothschild. So yes, this is the Ronald Graham. Have you heard of him? Okay, so again, we've got a finite alphabet A, but we're going to put in more variables, basically. So to make the notation easier, I'm just going to number it. So we've got variables x1, x2, x3, etc. Right, so a countably infinite number of variables. Okay. Then we're going to look at what are called m parameter words. Okay, so this W sub m is going to be words which have up to m variables, basically. So A union X m. Right, so all possible words made out of this set. It's not all the words. We're only going to allow ones which all of the variables appear, or the first m variables appear, and their first appearances are in increasing order. So what I mean by that is, okay, let's suppose our alphabet is like numbers, to make it easy, and a set of natural numbers. So something like 2x1, 3x2, x1. This would be an okay variable word, right? The first time that each variable appears, those are in increasing order, right? We get the x1 first and then x2. Okay. So that is in a set of 2 parameter words. What's not allowed is something like this, where the second one appears first, right? Because if you think about it, this is essentially the same thing as if we just made this one x1. Right? There's really no difference apart from numbering the variables. So it just makes sense to number them in a way so that these appear in increasing order. Right. The other reason for that is that Ramsey theory type statements can fail for stupid reasons, like if there's non-trivial automorphisms of your structure. Okay, which would be like an example of that would be exchanging x1 and x2. And then you can screw up your coloring just by mapping it through that automorphism. You can always color it in a way that it's not going to be monochromatic. Right? So we want to exclude things like that. Yeah. That doesn't make sense, don't worry.
Because you can color based on what the first lab will appear.
Yeah, right. And then you could ensure that, well, you'd never be able to find a monochromatic subject, but sort of for a stupid reason. Right? Because you can just switch the variables. Substitution. So it's similar to this, except we're not just replacing them with letters anymore of our alphabet. We could also replace them with other variable words. So we could replace some of the variables with other variables, is the idea. Okay. So if we have W, an m parameter word, and we have B, a k parameter word, which has length m. Okay, you can see where this is going. So the substitution, so we could substitute V into W, and what we'd do is replace every occurrence of xi with the ith character of v. So xi goes to ith character of v. Do you want an example? Does that make sense? Okay. So if v is just a word, it has no variables, then what we get out would again be just a word with no variables, right? But the idea is we could put in like a 2-variable word into a 3-variable word, and then we're just losing one of the variables. So this would be an element of wk. It's going to have k variables. Okay, so that's the substitution map. And then Rothschild theorem is for any k less than or equal to m, and any finite coloring of the k parameter words, wk, there is a word, an m parameter word, such that same idea as over here. So all substitutions to the set wv, which the v is going to be a k parameter word, and as above, it's going to have length m, right? Basically, any possible substitution you can make into here gives you the same color. Okay? So we can always find a word with this property. In general, this is probably going to be a very long word, right? Especially if we have a lot of colors. But you can always find a word. So I guess it's the infinity of these. Like each of these is infinite. Yeah, each of them is infinite. So you got a lot to work with. That's what allows you to find such a word that makes this work. So can anyone see how to get the Hales-Jewett theorem back from this? No? Hales-Jewett is the case when k equals 0 and m equals 1. Yeah, because then we're coloring 0 parameter words, which are just words. And then we're finding a 1 parameter word. Yeah. I should say this book is a good reference on a lot of these things. So this has a section on the Hales-Jewett theorem, as well as Todorovich's book, which is Introduction to Ramsey Spaces, or this one, which Martino wrote, Non-Standard Methods in Ramsey Theory and Combinatorial Theory. I don't think either book includes the Rothschild theorem, so that's that third reference down there, Ramsey Theory for Product Spaces, if you're interested in that. Cool. But again, there's an infinitary version of this, which is the same idea, but instead of finding a single word, now we can find a sequence of m parameter words, such that this is where the notation gets really messy. So again, any product of a finite subsequence and any possible substitutions into that, you always get the same color.
You mean that anything.
Cool. There's not enough letters in the alphabet to do Ramsey theory. Okay. So again, yeah, Hales Jewett is the case, K equals 0, N equals 1. Same thing, that will give you the infinity version of this. And again, you can get from here to here by compactness. Cool. All right, last theorem we'll see today. This one's called Gowers theorem, or sometimes called Gowers FINₖ theorem, and we'll talk about what FINₖ is. Okay, so if we have a function which, let's say it takes values in the natural numbers, then the support of the function is the set of points in the domain where the function is non-zero. Okay. Maybe I should have said that for us the natural numbers include 0. Okay, so all the points where it's non-zero, that's the support. So what we're going to do is look at the functions with finite supports. So FINₖ is all the functions from n to the set 0 up to k, such that they have finite support, and they have to take k as a value. So fx equals k for some x. Okay, so if they don't take k as a value, then they're in the next one down. All right, so basically we just classify them as to where the maximum value is. Okay. That makes sense? So it's 0 except on a finite set. So there is some point beyond which it's always 0. Okay. Now we're going to make each of these a semigroup in maybe the most obvious way. There might be a couple obvious ways, but so the semigroup operation is going to be pointwise sum. Okay, but only sometimes. So this is a partial semigroup. So that's only defined if they have disjoint supports. Okay. So they're never non-zero at the same point, right? And then you can see that their pointwise sum would again be in the same thing. Right, the sum's never going to exceed k. Cool. That's an adequate semigroup. Again, exercise the reader. Right, adequate meaning every finite subset you can find another element such that the products are always finite. Our homomorphism here is going to be what's called the tetris operation. Okay. I'll give you the definition, but so the tetris operation would go from fin k plus 1 to fin k. It goes downwards. And basically, I'll draw a picture, it'll make more sense. But it's what you think of in Tetris, you're removing the bottom line. Okay. So you can write that as max of fn minus 1 and 0. Okay, but the picture is if we've got a function like this, then what we're going to do You guys have played Tetris, right? We're going to take off the bottom layer, right? So that will give us, I drew that too big. It's going to look like that. Okay. Just like in Tetris, you take off the bottom layer, and then we're just left with this part. Okay? So everything falls down. Okay. So now, Gowers theorem says that for every finite coloring of fin K, so we'll fix K, for every finite coloring of fin K, there is a sequence inside okay, it's going to be inside fin M, where M is greater than or equal. Okay.
What's the quantifier?
Yeah.
For rolling?
Yeah. It's true for any K and M. So, okay, you should fix K and M back here. Okay. So for any finite coloring of fin K, we can find a sequence in fin M, which is above it. And then basically, whenever you apply this Tetris operation to bring it down to fin K, you always get the same color. Okay. So I'm going to write it out. It would be like so here this denotes iterating this operation. Right? So continually taking off the bottom layer. Yeah. So whenever this is in fin K, you always get the same color. That's the other. And I guess again you could use compactness to get a finite version of this, but you never see the finite version.
So why are the MI, why do they vary? Isn't it always M minus K?
Well, you could apply it more times to one of the parts, and then you add it to another part, which does take an extra value. So, but I guess they all have to be at least n minus K. Okay, but one of them has to be exactly n minus K to ensure the sum is n minus K. Yeah, don't worry too much about that one. It's sort of complex. Okay, but Martino came up with a slight generalization of this a couple years ago. So that's that fourth reference there, 2017. So this original theorem dates back to the 90s. This generalization is more recent. All you're changing is the possible operations you allow. Okay. So in this case, we were only allowed to take off the bottom layer, but you can look at generalized Tetris operations where you can take out any number of layers. That's the most intuitive way to think about it. So generalized Tetris operations. So basically, for any non-decreasing surjection from n to n. So let's say weakly increasing surjection. Then that gives you some sort of generalized Tetris operation. And it just acts on these functions by composition. Right. In fact, so this also holds for these more general Tetris operations. maybe you've noticed that all of these theorems that we're talking about sort of have a common theme to them, right? They all have similar looking structure. The only thing that's really varying behind the scenes is the semigroup question. So we can generalize all of these ideas to a setting which is known as layered semigroups. Basically what it sounds like, okay? Just to fix some of the things, so as a subset of a semigroup is called a subsemigroup if it's also a semigroup under the same operation. And that's pretty standard. We also have this notion of ideals in a semigroup, which is like the notion from ring theory, right? Which means for all elements of the ideal, all I and I and all S and S, then I product with S and S product with I are both elements of I. So the ideal absorbs elements of S. Okay. So here's our definition. So an omega layered semigroup, or just a layered semigroup, it's a semigroup S with an ordered partition. So we partition it into countably many parts, countably infinite number of parts. So semigroup, split it into infinitely many parts, and we want them to have two properties. So if we say Ti is the union of all the parts up to I, if you like, then that has to be a sub semigroup. The other property is that Si is an ideal of Ti. Okay? I'll draw a picture for you. So basically, we split it into layers sort of like this. Right, keeps going, keeps going. And the idea is that at each stage, what we've got in here, everything below any layer is going to be a semigroup, a sub-semigroup, right? So basically you can't, if you're inside this part up to S2, you can't get outside by the operation, right? And then each of these rings is an ideal of the interior of it, all the parts inside it. I guess the point is that those two examples we looked at, the Gowers semigroup and the Graham-Rothschild example, they are both examples of it. So I'll leave you to think about that, but all of these conditions are cool. Cool. The punchline is, maybe I'll be able to talk a bit more about it another time, but basically we can generalize all of these theorems we got to this general setting, and essentially the same argument works, right? So all of these theorems have the same sort of structure, and we can generalize it to this, which is what we've been working on.